In this segment, we're going to talk about turbines, compressors, and pumps. So what you see here, you've got a turbine, and as your working fluid moves from left to right, from the inlet to the outlet, it passes over a series of rotating blades. So as your working fluid expands and decreases in pressure, it causes those blades to rotate. And so you have shaft work being generated as your working fluid passes on through. So your enthalpy decreases, your temperature decreases because you're transferring energy out of the system in the form of work. So your enthalpy and your temperature are going to decrease as that happens, and the pressure also decreases during that expansion process. In this class, this is the way that I draw a turbine. So I've got things coming in at the skinny end and things leaving at the fat end. So I draw it rather simply in the class. Compressor is also, it's sort of similar, except instead of an expansion process, you've got a compression process. So as your working fluid passes through here, you put work into the system to cause a series of blades to rotate, and as they rotate, they compress the gas. So this is a process that will require work as opposed to in a turbine where you're generating work. So in this case, the enthalpy is going to be increasing, the temperature is going to be increasing, and because it's a compression process, your pressure increases as well. The schematic of a compressor that I use is very similar to the one for a turbine. It's just kind of flipped. So I've got things going in at the fat end and entering or exiting at the skinny end. A pump is a compressor as well, but we call it a pump when we're compressing a liquid. If you call it a compressor, you're indicating that you're compressing a gas. And they're analyzed the exact same way, although their design is a little bit different. So there are different designs for pump. This is a centrifugal pump, but you put power into it. You provide work to the system to compress the gas or compress the liquid from one pressure to another. So you see that the enthalpy increases, the temperature increases slightly, and the pressure will increase as well during this process. And the schematic of a pump that I use in this class is just a circle with something coming in and something going out. All right, so let's analyze these devices. So this is an analysis for a turbine, a compressor, and a pump for one inlet and one outlet. We'll work some problems in this class for turbines with multiple outlets, and those will be analyzed just a little bit differently. So one inlet, one outlet devices first. So first thing we're going to do is apply our conservation of mass. So here's our conservation of mass, and now I'm going to apply some appropriate assumptions. So number one, I'm going to go ahead and model this as steady state just to make my life simpler. And like I said, most of the problems in this class are going to be steady state processes. So that dm/dt goes away, and I see that this just kind of boils down to the mass flow rate at the inlet of this device is going to be equal to the mass flow rate at the outlet, and I just drop the subscript and call it m dot. Okay, so now I've got that, and now I need to apply my first law. So it's an open system because I've got stuff coming in and stuff coming out. So there's my first law, my conservation of energy. And I'm going to go ahead and get rid of that dE/dt because it's a steady state process. And now I'm going to look at some of the commonly applied assumptions for turbines, compressors, and pumps. So this is for all three of those. Number one, typically these devices are going to be insulated. And so if you're not provided a heat transfer rate for the problem, you could go ahead and assume that Q dot is approximately 0. It won't be, but you, like I said, you typically insulate these to minimize any heat transfer. Kinetic energy, same thing. Most of the time, well, I won't say most of the time, but in processes that would involve turbines for power production, your kinetic energy would not change that much. But there are some applications where the kinetic energy would change appreciably, and in that case, you would be told not to ignore those effects. Change in potential energy. It's pretty obvious that maybe you've got like a really small potential energy change, maybe not at all. So if you draw your control volume around the device itself, your potential energy change should be pretty negligible. So with all those assumptions being thrown in, the only things that I have left are my W dot term, the M dots, and the H's. So I've got W dot is equal to, I've got M dot 1 and H1, that's my inlet, and M dot 2 and H2 at the outlet. And of course, I remember from my conservation of mass that mass flow rate is the same at the inlet and the outlet, so it's just M dot times H1 minus H2. So looking at that turbine, since that's a power generating device, you would expect that W dot term, it should be, if you were using sign convention, that would be a positive number, right? So your W dot should be a positive number for a turbine, unlike a compressor and a pump, which require work. So you're putting work into the system, and so those would be negative numbers. All right, well, I hope that was useful, and thank you for watching.